Well, thank you very much for attending my talk. My name is Jules Damji. As Omar introduced me, I'm delighted to be here back on my old stomping grounds. This happens to be my 14th Spark Summit where I'm presenting. And so I'm delighted to be among friends, among other advocates, among Spark community, from whom I've learned quite a bit. And so feel really great to be back here on stage, sharing some knowledge from a different angle and from a different lens as well. Who am I? As lead developer at Anyscale, where as part of the Ray team, senior developer advocate at Databricks, I was there for about 6 years, led developer advocacy efforts at Hortonworks, and prior to that, I was doing a lot of coding and engineering, and have had the good fortune and privilege to work at some of these very notable companies who really changed the world, and I keep on continuing being at the right place at the right moment, and I've been very, very fortunate with that. And I'm also co-author of the Learning Spark, the second edition, along with some of my advocates who are either here today or I'm going to be meeting them after a short break of 2 years under house arrest, but I'm definitely back on action and on stage. Who do I work for? I work for a company called Anyscale. We are the original creators of Ray, and Ray is an open source project, which is a distributed computing that was developed at RISELab, which is the former lab called AmpLab, where notable innovations happen, such as Spark and Mesos. So we do share a historical pedigree of technical and academic brilliance. So delighted to be part of that particular pedigree. And what we do is, like any other open source project, we offer a managed service for our enterprises. And our mission is rather simple. We do want to distribute computing, make it easier for everyone, because the future is here, which is distributed computing. And we want to be able to scale your machine learning workloads. And you heard about what Max talked about. When you're doing time series, you really have to do scale. So that's who I am, and who I work for. Now, why you're here today? I want to take you on a journey starting at 20,000 feet to give you a motivation of why Ray and what Ray ecosystem is all about. And then we'll drop down to about 10,000 feet while I talk about Ray architecture and its components. And then we'll get down to the 0 feet above sea level. We'll look at some code, we'll look at some APIs, and design patterns that make Ray possible to scale at which you actually want to scale your machine learning workloads. And I'll focus on one library, which is very common when you're actually building models, called RayTune. We start optimizing things, and if time permits, given that I've tried to do this, if time permits, I'll try to do the demo where I show us how you can actually do these workloads. And then hopefully I have prepared answers for your questions. As Henry Kissinger would say, do you have any questions for my prepared answers? So hopefully I have time for that. So why Ray? What's the motivation behind that? And when Ray was being conceived at RISELab, the researchers were looking at, in a very prescient way, what were some of the fundamental industry trends that actually led to the information of advocating and building Ray. And one was the insight into that machine learning has become rather pervasive. It's so much pervasive that it's entered in each and every sector of industry. And as a need of that, because of that particular pervasiveness, distributed computing has become a necessity. It's no longer an exception, it is a norm now today. And in order to do that, you have to be able to actually make these paradigm rather very easy. And then finally, nobody would dispute today if I made the claim that Python is the de facto language for machine learning and data science. And you heard today at the keynotes that how Python has actually become a central sort of magnet where a lot of other technologies provide APIs and work with. So let's look at the one. When I talk about pervasiveness, it's across the board. If you go into fintech, today you heard about Max talking about forecasting. We build prediction models that actually work at massive scale. Transportation has completely changed because of the autonomous vehicles and the computer vision recognition and all these different use cases that are actually being unleashed day and day after. And all these different industries, require you to do scaling at a massive scale. And this is because of the blessings of scale, right? Scale is an important element when you're actually dealing in machine learning models, especially when you're building foundational models. We're building large language models. And this particular graph I just borrowed from The Economist in a very timely manner, where they talk about the foundational models and the future of AI. And if you look at these models that are on the far upper right side, take about billions of floating-point operations that require for you to actually do the computations in 1 second. If you just get your laptop, that can do a couple of billion of instructions per second. But when you start scaling those models at that, this is where the blessings of scale come in. And likewise, if you look at this particular diagram, this sort of blessings of scale introduces another problem, which is this compute demand supply problem. Now, if you look at all the models on the far right, you see that's the amount of petaflops it actually requires for you to train this particular model. And the CPU somehow falls short. Now, you might argue that we have provided you with all these hardware accelerators that actually can meet the demand, but they still fall short, right? There's a big gap between what the TPU can provide and what the actual scaling that it requires. And our contention, and the contention of the people who actually were working in the researchers at the time, was that the only way you can actually do that is to go in a fully distributed manner. And that's sort of the second fundamental trend that informed into the evolution of Ray. And then finally, the Ray data ecosystem is just, the Python ecosystem is indisputable. If you're a data scientist and if you've been working in that particular field, on the left-hand side, these are all the Python data libraries that you use constantly and invariably to build your models or to do some sort of analysis or to do some sort of an EDA. And if you're doing deep learning programming, you have all these on the right-hand side. And invariably, all of them actually have some sort of a Python binding. So those are sort of the three things that actually led to the evolution of Ray. So I talked about the motivations. I talked about why Ray. Now what is Ray, right? Now let's get down into the fundamentals of why and what is Ray. And there are three things, really. One is it's a general purpose, universal library that allows you to do distributed computing. And it's possible because it actually provides you very fundamental primitive abstractions that you can actually easily take your existing code and then convert them into a distributed fashion. It offers you native libraries using these primitives to scale your ML workloads, and we'll talk about what those libraries are. And finally, it can actually run anywhere. In other words, you can run on a laptop, you can run on your public cloud, on Kubernetes, and on premise. And I like to visualize it, Ray, because when I'm a visual person. When I look at it as a layered cake of functionality and capabilities for scaling your common machine workloads. So if I look at this architectural diagram, at the bottom, you actually have your public clouds and the places where this infrastructure can run or this framework can actually run. So across your public cloud. The middle part is the core, right? This is the middle part, which is the distributed framework that gives you primitive abstractions for you to write your distributed applications. You don't have a reason, you don't have to worry about, how am I going to scale, or how am I going to worry about performance, or how am I going to worry about scheduling, or how am I going to worry about elasticity. Ray takes care of it. And that's the embodiment and the philosophy of Ray, is that we provide you with simple primitives for you to be able to take your Python applications that you have and convert them into distributed manner at scale. And we worry about the plumbing and all the hard stuff. And then if you go one layer above, you have the native libraries. The native libraries, one on the left-hand side, are built atop using those primitives to allow you to scale your libraries. And these other ones in the middle are all libraries that have been integrated as part of the ecosystem, so they work equally well with you if you actually want to convert them into that. And if you don't care about machine learning, if you don't care about anything else, if you're one of those guys who just want to scale your Python simulations at the massive scale, then you can actually use you can build your own library and run on top of Ray. So that sort of gives you the high-level view of the layered cake of functionality. And the workloads, which are very common, that all of you who are data scientists and machine learning are invariably dealing with it every day, are you're doing data processing. So if you're doing that, you can actually use array datasets that allow you to do the last mile ingestion into your training set at scale, whether you're using it with modem or whether you're using Mars, if you're using Dark-Schooner, you can actually use those libraries to ingest your data at massive scale into your data pipeline for training. If you're using deep distributed training learning, you can actually use RayTrain, and it works well with PyTorch, with TensorFlow, TF-configs, distributed parallel programming, as well as if you actually want to use Horovod. If you want to use scikit-learn to just distribute your jobs, we have a drop-in replacement for that. And if you've been building models and you're using repositories such as weights and biases, MLflow, or Comet, and now you want to take that particular model and deploy it on Ray, so we have integrations that allow you to do that. And we have integrations in your training that actually have hooks that can work with MLflow to do your experimentation. And Tune is an important part, right? Tune is really an important element of scaling your workload. So if you're doing hyperparameter tuning, you can actually use RayTune, which is integrated with, if you're familiar with HyperOpt, you can actually use those libraries. And those of you who are into reinforcement learning, RLlib is one of the notable libraries that allow you to actually do that. So those are the libraries that allow you to scale that. And then we'll get into one of the libraries, and hopefully I'll be able to show you a demo on that. So that sort of is, at the essence, at a high level, the layered cake of functionality and the native libraries which are built on top of Ray that allow you to scale those things. Now, who are the people who are using it? Obviously, no slide goes without telling you that, hey, listen, there are people who are actually using it. We're just not existing in the vacuum. There's notable companies actually using it at a massive scale. If you want to hear more about what they are using and how they are using it, you can actually go to a website, ray.io, and they will has blogs on it, and they have user stories about in what form, in what machine workloads, libraries they talk about they use to scale their use cases. Now I'm going to drop down a little bit further and talk about the Ray architecture and its components and how things actually work behind the scenes. I think it's important to have that lens into the framework that you're actually going to use. Now, if you're familiar with some of the distributed frameworks that you probably have used before, there are some components which are similar. There are some components which are quite unique. But invariably, all of them actually have some way where you can actually scale things. So on a worker node, on a Ray cluster, you will have worker processes. And these are worker processes that will be equivalent to about the number of cores you actually have. So each of these Ray cluster will have this worker nodes. And there is a process called RLlet, which is a C++ program that actually has two threads, which are very important in managing that particular process. One is a scheduler, and the other one is an object store. And these communicate across the entire cluster. And on the head node, you have two distinct processes running. One is called a driver, and the other one is called a global object store. Now, those can actually run anywhere. We just, by convention, actually run it on the head node. And the global store is really the brain that actually has all the metadata about who's running what, where the tasks are running, what actors are running, what are the object references, who actually has what resources, and what the current state of all those tasks are. And these are updated on every heartbeat so that the cluster at one point, or any point, knows exactly who's doing what and what its resources look like. And this is something quite unique. It's quite distinct about Ray because there's not a central bottleneck where you're actually doing the scheduling. The scheduling is done in a very distributed manner. And the object store is very distributed across the entire cluster that allows you to share those objects. And if I go one level below, you can actually see how these things work. So your tasks, now talk about what those tasks and actors are implemented and they run in a very distributed manner on each and every worker. And the object store is where RLlet gets and finds out who has actually has got what resources. I can schedule a particular task on that, and the object store is actually updated by this. So there's a lot of communication going on between that. And collectively, it sort of gives you the distributed scheduling capabilities, which is quite unique to Ray, and the distributed object store, which is based on top of Plasma using arrow objects. It's quite efficient. So that is the anatomy of what a Ray cluster looks like. Now I want to shift the focus a little bit and now go down into the primitives that allow you to do this distributed application at scale, which we call design patterns. Now those of you who are software engineers probably have heard about what these design patterns are, right? This was first introduced by the Gango 4 in this compendium book. And design patterns are sort of language constructs that nudge you or that encourage you to use a language in a manner that gives you the most efficient way to write something. They're like parts of English grammar, where you have participles and you have phrases, and the diction and the grammar dictates how you actually put those sentences together. Design patterns are how you actually put your code together. And array design patterns have three very common, which are pervasive across the entire native libraries. One is array parallel tasks that allow you to take the existing functions that you have and convert them in a distributed manner in a stateless across the cluster. The second one is features, and features, you have heard about them. You know, Python has features, Scala has features, C++ has features, and these are objects that can contain a value sometime in the future. And the reason we actually use those features because this enables us to fan out massive amount of tasks and return the features right away in the anticipation that at some point in the time you will actually need the value of that, and you can actually get those later down the road. Array actors are the stateful part of array pattern that you can actually take an existing class that you actually might have and convert that into a stateful service. And once you actually have your stateful service, the state, the methods that you actually might implement in the class could be actually used as methods they would invoke, to which you can actually send state, or to which you can actually send messages. So that sort of provides you the ability to write stateful services in a distributed manner. Something very similar to if you're familiar with Akka and you're familiar with some of the other design patterns where actors are actually used. So how do they look like in Python? Well, you can take a function that you actually have, convert it into a task, which is going to be executed on a node. You can take an existing class that you might have, convert that into an actor, and then putting on a node. And then you have an object that any of these two entities that might create that can be stored in this distributed immutable object, which you can actually fetch when they are available for you by just calling array primitive to array.get. So let's look at some code. How does the code look like? I have a function that reads an array from a file and then returns a numpy array. And I have another function called add that just takes two numpy arrays and adds them together and returns a particular value, right? Now, when I use that in my code, all I have to do to convert them into distributed fashion is to use array.remote as a decorator, and I'm ready to go. And this will be executed anywhere on the cluster. And the way I use them, just put the suffix remote and give the argument, and it just returns me an object reference right away. And when I'm ready to get the value of the final result, all I do is do array.get. Simple API. All you have to worry about is just using those in the manner, and you're ready to go. You can take a class that actually have and convert that into a stateful service by using a decorator. And if the decorator or if your class requires certain resources, I can specify that I want the number of CPUs to be 1, or I can use a fractional CPUs like 0.57, and it will allocate that GPU or CPU for that particular task. And I have methods that I define. And when I want to use these methods, all I use is the instance variable, its method, and the remote function. So how does it actually translate in the back end? So when I execute the function called read.ray, it's going to be scheduled on a node 1, and it will read that particular file whenever the resources are available. The second one is going to be on the second node, and it's going to read this particular file. It creates a dynamic graph, because that's very important, how graphs are actually created. And then the result, the third function, add, could be scheduled somewhere else, and is going to do an add and return you the result. And the result is returned back with a reference, and all I do is just do array.get, and I get that. And that's a final call, which is actually blocked. So this allows you to actually create all these tasks asynchronously, and then you can actually do a get on one of them. And then all the execution is done for you. I didn't have to worry about where the socket is. I didn't have to worry about where it's going to be executed. All that is taken care of me. I'm just writing simple Python code. And that's what actually makes the array so simple to use. And that's actually the beauty of it. And the last, but not least, is the distributed object store, which I talked about features. And you can think of it, each and every node has its worker processes which are running. So if you have 12 cores, you'll have 12 worker processes by default running. And there's a shared memory, which is a Plasma Apache Arrow built on top. So it's a very efficient way to store your data structure. And it is the shared memory. And if you have processes running on that particular node, they can actually share the values that was a 0 copy. So there's no IPC going on between the processes. There's no context switching going on. I can just do a 0 copy, go straight into shared memory, get the value that I need. So if my function X is running on worker process 1 and function B is running on thun, and both create X and Y, I can actually share those variables very easily. And if the shared memory runs out of space, there's a way algorithm that actually spills it on the disk, and the object store is updated to find out if you want object reference X. It's now sitting on object node Z. You can actually go and get the value of it. So that are the things behind the scene. So here's how distributed object store works. Think about node 1 as a function F. It returns the value X. I have another function called G. It returns the value Y. I invoke the function F that returns me the reference IDX. I send it to G. Now, Ray is smart enough to use data locality to say, okay, function X has created an object reference X. I know where object reference X is on node Y, so I'm going to schedule the G function on node G. So now I don't have to do extra copies of whatever the variable is. I'm just going to use my 0 copy and get it straight from the object store. So these are little things that Ray can actually do to actually make tasks a lot faster. So that was sort of the object distributed store. So I gave you the 10,000 view of what and why Ray. We went into what the object components are. We talked about the APIs and the abstractions that allow you to do that. And now I'm going to talk about one of the common libraries that people actually use to scale their machine learning workloads. And tuning is something quite common. If you're going to build a particular model, you're going to tune the particular model. You want to get the best model. You heard what Max talked about today, that hyperparameter tuning is an important part in training the boss model. You will hear that quite often as a narrative in almost anybody who's actually building the model. So why Ray Tune? Quite simple, really. It offers state-of-the-art algorithms straight out of the box. Any of the sort of algorithms that you actually want to use to search your hyperparameter space, it actually gives you that right away. Because it runs on Ray, it gives you fault tolerance and elasticity very easily. So the Ray autoscaler can automatically create new worker nodes on which you can actually create more trials if you actually want it, or you can actually bring down. So elasticity is important, and there's fault tolerance involved with that as well. And you can run it on your laptop if you actually wanted to create trials. You can run it on a multi-node, multi-cores, if you actually want to do it. So there's a flexibility to that, because Ray allows you to be able to do that. And finally, it's quite interoperable with other native libraries that I talked about, such as Ray Datasets and Ray Train and RLlib and Ray Tune. And the next version of these native libraries has sort of evolved into what we call Ray Air. That's going to be colleagues of mine. Anthony was here today, is going to be giving a talk at 4:45. So if you hear about what's the next coming in Ray 2.0, which will be coming out sometime in the summer, that's where we have sort of taken it to the next level, where these libraries are very, very interoperable and very easy to use. So that's sort of next level. So these are some of the libraries. If you're familiar with hyperparameter tuning, you can actually use these search algorithms along with the compatible schedulers that you have, and you can combine and mix them very easily by just using very simple line of code. The RayTune API is so intuitive that I just specify I want to use Optuma for my search, and I will use Asha scheduler, and you go off to the tracks with it. So that's sort of the search algorithm and trial schedulers. Now, for those who are probably new, or those who are not familiar, what are hyperparameters? That we keep on hearing it as if it's a buzzword. And there's a difference between hyperparameters and modal parameters. And hyperparameters are something that's actually set, are normally set before the training. And those could be, for example, your learning rate, or it could be the type of modal architecture you're using for a neural net. It could be your filters. It could be any one of the parameters that you actually set where you actually want to define what your model is going to look like. It could be a learning rate. And these hyperparameters somehow dictate how the model parameters are going to be learned and going to be computed. For regression, it could be just model coefficients. For neural network, it could be weights and biases. And here's a very sort of an example of what your typical neural network looks like. And all the numbers that you actually see are the hyperparameters you're going to use to train your model, to tune it, to make sure that you actually get the best metric, you bring down the loss. Now, you can probably surmise from this that your hyperparameter space can actually grow rather really far, and it can really be huge. And how do you actually deal with that? And as a result, there are some challenges involved when you're doing hyperparameter tuning at the massive scale, right? It is time consuming. You heard what Max was talking about, that it can actually take anywhere from seconds to days to minutes. And as a result of that, because you're using cloud resources, time is important in the cloud. And so you're actually spending resources available, whether it's GPU or whether it's CPU. And you want to make sure that when you're doing hyperparameter tuning, it's elastic and it's fault tolerant, so that if you started a trial that's going to last for a couple of hours and one of the trials fails, do you start everything from scratch, or do you actually start from where you left off? And Tune gives you a couple of algorithms that mitigates and helps you with the strategies. One is, as I say, there are all these sort of algorithms you can actually use straight out of the box, and you can swap them quite easily by just combining the different search algorithms along with the schedulers that will run efficiently and try to mitigate the time constraint. But it offers you sort of three search strategies that you can actually employ based on how big your hyperparameter space is. First is the grid search and random search. Most of you are familiar. If you actually come from the scikit-learn background, you have these ways where you can actually provide your config space, where the grid search is a combination of discrete values that you provide, and it's going to launch those in parallel, each and every distinct combination, to find out what's the best fit. Or you can use random search, where you uniformly go across a certain hyperparameter space and try each and every combination randomly to do that. Those are very easy because they're very easily parallelizable. Array allows you to actually do that. And the second one, the only problem with this is that you might be going down some bad configurations that would allow you to do that. So you don't really have no choice in saying, well, which are the bad configurations? I can't really figure out. You have to sort of brute forcefully go with that. This is fine for a small hyperparameter space, but it can get a bit expensive if it's very large, because you're training using brute force to actually compute all those. The second one is more sort of using Gaussian processes, which is called Bayesian optimization. What it actually does, that it runs in a very sequential manner, and it keeps track of the previous ones before it actually decides to launch the new one, and uses Gaussian processes to create boundaries, whereby saying, I think these set of hyperparameters that I have, I think look very promising. I'm going to cluster them together. The rest of them, I'm just going to discard them and put them in the bin. And this is something that you can actually use that. Now, there are popular libraries that actually support that. For example, HyperOpenOptuna and Scikit Optimize. Recent literature actually has given some numbers that you can actually use that. And then finally, the third one is using sort of advanced scheduling mechanisms, whereby you can fan out all these parallel trials, but you use early stopping using successive halving. So you create all these rungs of different hyperparameter combinations you want to run, and you keep on trimming as you go along the rung to find out which are the ones which are bad performing, which are the ones which are promising, and you keep on following the one who actually gives you the best results. And that sort of mitigates the whole thing. Well, how does that actually work? Very simple. When you're using RayTune, there are 3 steps involved. You create your training function, and the training function is no different from any function that you would use today for XGBoost or for scikit-learn or for PyTorch, which is a function that's iterating over epochs and computing the loss. So you define your training function. You provide the training function as part of the argument to RayTune, and you provide your config space and the sample that you actually want to use, the search algorithm you want to use, and the scheduler you want to use, and you just say run.tune. And now run.tune is going to run on Ray, and the driver process is the orchestrator, which is created as an actor, and it actually creates that actor, and now it's going to actually create all these different worker processes, and each worker processes, or each actor on the worker process will have a copy of your training function along with the unique combination of your hyperparameter space, and it will run, right? It will run across the entire cluster. And every now and then, it's going to report the metrics back by saying, hey, this is what the metric was for this particular trial run. And the driver process is going to decide, and I'm going to stop that using early trial if I'm using ASHA algorithm, or if you're using half successive scheduler to say, this is not doing well, I'm just going to chuck it and stop it. And I'm going to launch a particular new trial, and then off it goes. And then periodically, you can actually define how often do you want to do a checkpoints, whether you want to do checkpoints at the end of each epoch or number of epochs. And then should something go wrong, which invariably every time something does go wrong, your worker process dies, we can actually restore that from the checkpoint, and off we go and start that. So that's sort of the hyperparameter tuning, and that's sort of the end of the talk on ray tune. Just quick takeaway. Distributed computing is necessary today. I told you, I made the justification why it's necessary, because we're entering a zeitgeist of ML, and things are very normal now to actually do distributed computing. And Ray's vision is to make those things very simple by just using those decorators. And we are providing libraries for you to actually scale your particular machine workloads. If you want to learn more about Ray, just get involved with us. We have regular meetups that I run on a monthly basis. We have Slack channel. We have a GitHub, close to 700 contributors. Follow us on Twitter, and we'll follow you back. I know it sounds dodgy, but we'll do. Thank you. And I think I have 4 minutes. Now, I have a choice. Do you want me to do a demo, or you want me to take Q&A? Oh, love it. Brilliant. All right. So, those of you who have questions, we're going to be out here, but there are a bunch of us from Inniskin and Ray team. We can actually chat. So what I'm going to do is 4 minutes, see if I can actually beat the time. I'm going to use 3 training workloads. One is training, normally, obviously. I'm going to do hyperparameter tuning. I'm going to do inferencing. And what I'm going to do is I'm going to run something on one node, and then I'm going to run it on a distributed array node, and then look at the figures. I have about 10 million rows of classification. I got about 40 features and 2 classes. There's some code over here that just preliminary code that actually loads these different data sets of 300 megabytes, 3 gigabyte, and 11 gigabyte. This is my training regular XGBoost function. Nothing natural, unusual about it. I define my parameters. I use a training boost. I load the Parquet files using the typical. I convert them into the matrix using the D matrix, right? And then I just use train to do that. I run it. And I ran this a minute ago because I think Wi-Fi is a bit dodgy over here. And I just wanted to try with my 300 megabyte to see actually what it is. And it took about 9 seconds just to make sure things are actually working. And then I tried to run it on my 3 gigabyte file using normal XGBoost, right? I'm just not going to use Ray at all over here. This is normal do. And I ran that, and it took about 134 seconds, right? Then I do the same thing using XGBoost. And XGBoost on Ray is a replacement whereby now we actually take the data that we actually have, and we shard it across using Ray datasets to each and every trainer. And each and every trainer will get a copy of that particular model and will train on that particular data. And then it will actually resync all the gradients using Rabbit protocol for Ray XGBoost. And this is all handled by the tracker that actually keeps track of. And remember when I was talking about it actually keeps track of all the matrices, and this actually happens in a distributed manner. And the code is exactly the same. I'm using my XGBoost parameters over here. I'm using the function. The only difference I'm doing is I'm importing from XGBoost Ray the Ray matrix, which is the distributed way to have my data across. I'm using a train function, which is the train replacement for Ray. And the Ray parameters, how do I actually want this to be how do I want it to be parallelized? And those are only 3 lines of code, nothing else, right? And I'm using exactly the same function. And when I ran this, this is going to run across my entire cluster, and it took about 16 seconds to do that. So you can actually see the comparison between 130 and 16 seconds using 8 CPUs and 8 actors across, because I provided the distribution of using 8 actors and 16 CPUs. It's going to use that across that. So that was training. So you can see that when I run that on a particular local one machine with 16 CPUs, took about almost 2 minutes. And when I ran that using Ray XGBoost, parallelizing, it took only 15, about 1/4 of the time. So that was the training node. Hyperparameter tuning, we talked about that. All I'm doing is exactly the same thing. I'm just providing my parameters that I want to scale across, my parameters that I want to parallelize, which I'm using 2 actors, 8 actors, and 2 CPUs for each of these, and I'm just sending it to tune. I just put the tune parameter, just invoke tune along with my training function that I have, my 3 GB files that I want to use, and the way I want to parallelize these trials across. And when I run it, let's see if I can actually run this here. I see I have a couple of minutes. Oh, I got 15 seconds. Anyway, this is going to run using all the 144 CPUs that I have across, and then return me the value. You can actually see that each and every trial was eventually completed, and then gives me the final best evaluation over here, which is this particular metric. So you went across, created my trial, did all the hyperparameter tuning across 8 actors or 8 nodes, across 16 clusters, across 16 cores, and then did my hyperparameter in parallel, and then return me the results. And then finally, when I want to do inference, I can do that on a regular XGBoost using 11 GB of file to do the prediction on that. Very simple. I've got the model that I've trained. I'm going to use the basic XGBoost on single node. And when I do the invocation of that, you can actually see that it took about 11 GB, about 80 seconds or 81 seconds. And when I use XGBoost on Ray, it's exactly the same thing. The only difference is that I'm now actually using a distributed Ray matrix to take my 11 GB and send the difference across. And when I actually run that, you can actually see this running across my entire cluster, doing inference in parallel. And this should probably take about 10 times faster than this. So it took 9 seconds, right? Compared to the other one. So what I essentially showed over here is you can actually use Ray to scale 3 workloads. You can actually use training to use XGBoost Ray to distribute your workload. Then I showed you how you can actually do hyperparameter tuning, which is a very common thing that people mostly do. And you can actually do that across your cluster by providing the hyperspace that you actually need. And then you can actually do the inference, whereby you can actually do prediction either by batch, or you can actually do that across. So that essentially was on the dot. Thanks a lot for choosing the demo. But if you have any questions, a bunch of us wearing the infamous Ray shirt, corner us outside. We'll be more than willing to answer any questions. If you want to find out what's the next version of Ray 2.0 coming up, attend my colleague's talk at 4:45 in this particular room. Thank you all for paying attention. I hope I wasn't a cure to your insomnia.